Okay, so we just have to draw the plausible mechanism and then justify the steps that we draw, and I will just explain them in Word. So comparing 1 and 2, I see the rest of the substituent are same except this leaving group is switched with a chloride, and then there's some stereochemistry going on here and there. Okay, so another thing you have to be aware is that we have a strong nucleophile. That's because you will see more in detail next chapter when we learn the elimination. And this is actually really weak base. It's a strong nucleophile but weak base, and anytime you see that, it's undergoing simply SN2. That's it. It's not going E2 because for elimination we need to have a strong base, or at least it has to be what the weak base and weak nucleophile. But we are in chapter 7, so substitution is very focused, and anytime you have a very strong nucleophile and then we have a secondary carbocation here, then it's likely to undergo either SN1 or SN2. But again, we have a really good nucleophile, so it's gonna go SN2. So having said that, and also we have a good leaving group, that's why. Okay, so having said that, so we identify the leaving group as this guy, and we need to form a bond between that nitrogen and that carbon over there. You see that OR substituent attached to the carbon, and it's just 1 unit apart. Therefore we need to form a bond, and then to form that bond we need to have a nucleophilic attack from that lone pair on above the nitrogen. And since I already identified this as the SN2 type reaction, so we need a concerted process in which the nucleophilic attack and the leaving group happens at the same time. Okay, the alpha carbon, and then in this way we are losing the leaving group. We have a double arrow. And we need to identify the minus charge over there. So when we draw this, we're gonna have dash. The reason is that anytime we have SN2, it's undergoing the inversion of stereochemistry. So since this is tethered reaction in which the nucleophilic center and then the substrate that bears the electrophilic center are in one structure, we have to conform to the change of stereochemistry. So we have a dash, and the nitrogen is gonna be positive because we have a four bond, and then because we have a dash between the carbon and nitrogen, and then there's a hidden implied hydrogen, then this is also a chiral center, the carbon above it, and we need to draw the wedge to show that carbon is one of the chiral center. Okay, and again, don't forget the plus sign on that nitrogen, and then draw the appropriate substituent. Okay, it looks good so far. Now we haven't used that chloride as our nucleophile, so this time I'm gonna use that. So here's our chloride ion. Again, it's a good nucleophile, and where is it gonna attack? See, in compound 2, I see it's attached to the carbon, and we just had that wedge bond between these two carbon. So the answer is obvious that he's going to attack this carbon, okay? And then in turn, we have to break this bond between this carbon and nitrogen. And where is that bond electron between nitrogen and carbon is going? Well, it has to fill up that the cation structure here. We have plus sign, right? So it has to land on the nitrogen atom. That way we no longer have plus charge. So if I draw this right, that pH stands for phenyl. That looks like that, in case you forgot. And that's it. There's nothing more to it, and we have an identical structure now. So we got to the answer. So in other words, we have a 2SN2 reaction that forms compound 2. The first SN2 happened intramolecular reaction, in which the lone pair on the nitrogen attacks the alpha carbon that bears the leaving group, and then second nucleophilic attack happened, SN2 happened with a chloride ion to break the bond between the nitrogen and the carbon in that triangle ring, because that's also very unstable with a plus charge, and then there will be a lot of angle strain going on. So chloride is come as a rescue, and we have stable forming compound 2. So that's it.